So in this lecture, I'll continue talking about ergodic theory in the category of continuous functions on compact metric spaces. So the one of the two main objects from a functional analysis point of view are first the space of continuous functions on the compact metric space. And it has a norm given by sometimes called the soup norm or the C0 norm. It's the maximum of the absolute value of alpha of x over the compact metric space. And notice we have a compact space, and so continuous functions have a compact image. In particular, the image is bounded in the real line, so there is a max that it's attained, and it's finite. And then we use the norm, as one usually does, to get a distance on the space of continuous functions as just the soup of the difference between the twos. And it's a basic theorem, which I will just quote and not prove for you, is that this makes this metric, this topological metric derived from the norm, makes it into a complete separable metric space. So as we've seen many times, separability in terms of having a countable collection of open sets is central to making a lot of ergodic theory arguments work. And there's a second structure, which is that it's also a vector space. Given two functions, you can add them pointwise and do scalar multiples. And so this makes putting the structures together, the topology and the norm, the complete here, which is again something you have to prove, we get a Banach space. And this R is sometimes suppressed and is just written as Cx, and sometimes this R is replaced with the complex numbers. But I'm going to probably just stick with the reals here. But you may need complex numbers if you're going to work with, for example, Fourier series, etc. So a probability measure, let's bring the measures back into the picture, defines a linear function from the space of continuous functions, or the observables, or the scalars, if you like, into the reals by the integral. All right, so in this context, integration just gives a linear functional. So functions from a vector space to the reals are usually called linear functionals. And notice it's what's called a bounded linear functional, because the magnitude of alpha is less than or equal. It's this integral triangle inequality, and alpha now is continuous. And this is then less than or equal to the max of alpha. This is standard analysis. You bring the max out in front, and you're left with the measure of x. Measure of x is 1 here, since we're always having probability measures. And so this just gives the zero norm of alpha as an upper bound. All right, so this makes L what's called a bounded linear functional. So that's where there's some m for which L alpha in magnitude is less than m times the norm of alpha naught. All right, so what this tells us is that each problem, now these are all probability measures, remember, Borel probability measures, defines a bounded linear functional. All right, so the next lemma says that these functionals characterize the measure. All right, so that's the first step in understanding how all these pieces, that if you know what the linear functional is doing, you know what the measure is. All right, so here's the formulation. Now we have a name for all Borel probability measures, which I probably should have defined at the beginning, but these are the objects we're thinking about. And we have two Borel probability measures, and they're equal if and only if their integral against all observables are equal. All right, so one way is trivial, right? If they're the same measure, then certainly they give the same integral. And for the other way, we have to remember, and that's why we did it last time, that you can find in the context of compact metric spaces, you have regular Borel measures are regular, and so we can compute the measure of a measurable set, as the supremum of all the measures of all the closed sets that live inside it. All right, so that being the case, if we could prove that this condition implies that mu and nu give the same measure to every closed set, then they would give rise to the same supremum. And so that would suffice. So we have reduced the problem to just showing that they give the same measure to closed sets, given this integral condition. So obviously what we have to do is use the closed sets to produce a observable or a measurable function, or an integrable function, well, continuous function as well. All right, so what do? Given epsilon bigger than 0, we use the regularity of the measure to find some open set U that contains C, and their measures are less than epsilon. All right, so I have a picture up here. Now we define the observable in the following way. We have our closed set, we have our open set, is that sitting out here in the complement of the open set, which of course is a closed set, we let the alpha be 0, and inside we interpolate between 1 on the closed set and 0 on the complement by this kind of fairly standard trick. We take the distance between x and the complement and divide it by this sum. So the topology yields that this denominator is never 0. And if you remember from your metric space theory, distance functions to closed sets is continuous. And so alpha is continuous. Remember, it's 0, so you have a matching at the boundary here. And it's also between 0 and 1. And it's equal to 0 on the complement and 1 on C. So the real line picture, if we draw a graph, it's 0 outside of C, it's 1 on C, and then it goes up and down in some monotonic fashion. All right, so what do we buy from that? Well, the function alpha is 1 on C, and it's positive. So that means if we integrate over the entire space, it's bigger than the integral of the indicator function of C. And so therefore, we can write this integral inequality like this. And by hypothesis, for all alpha, mu and nu give the same integral. Now, on the other hand, alpha is between 0 and 1. All right, so u can only have smaller nu measure, right? Because alpha is between 0 and 1 on u. All right, and so we can only get larger measure. This can only be smaller. So because it's 0 outside here, and so we can only get larger measure. And we know by the choices originally here, this measure is difference. And then a little argument says that mu of u is less than or equal to mu of C plus epsilon. All right, so now standard trick, true for all epsilon. So mu of C is less than or equal to nu of C. And there was nothing special about starting with nu here, mu, mu here. We could just as well started with nu, and therefore the reverse inequality is also proved, and therefore they're equal. All right, so this tells us that the linear functional, I think I summarized this at the start of the next slide here. So if we name the linear functional using the measure like this, then the linear functions are equal almost everywhere. Sorry, are equal everywhere. That implies the measures are equal. All right, and so the Riesz representation theorem, which is a little more general, I'm just stating the version that's good for probability measures, says that a big class of the kind of natural class of linear functionals are all constructed this way. All right, so we're still in the compact metric. If I don't say that through the whole lecture, we're compact metric. If we have a linear functional, All right, so I should really say this is a linear functional. We have a linear functional and it's positive. In other words, it's positive or non-negative. It's positive. This is called positive, which is non-negative on negative functions. All right, so if you think about this, it's a continuous function, so it has to be zero everywhere to have a zero integral. And we're also going to normalize them. So this is so it corresponds to a probability measure, and we want them to be bounded. Then there's some measure which represents it as its integral against the measure. All right, so it says that given these hypotheses on the linear functional, then there's some measure for which that linear functional is the integral against the measure. And of course, that's valid for all continuous observables or scalars. All right, so now we have something about linear functionals. We have something about this space. We don't have a topology on this space yet. We have a topology on this space of continuous functions. In fact, we have a Banach space structure on it. So now we need to also talk about measures. Now, probability measures, if we go into a larger class of signed measures, then we could get a vector space, but our focus here is on probability measures. All right, so the sum of two probability measures isn't a probability measure, all right, but in fact a convex combination is. So we're not going to get a vector space, but we're going to get a convex space. All right, so here's the topology we put on all Borel probability measures. So this quick way of saying is it's the smallest topology making each of the maps. So we fix an alpha, and that gives rise to mapping a measure to the integral against the measure. So that's a nice map. In fact, I won't say any properties of it, but the topology is the one that makes all those continuous, and you look at the smallest such topology. All right, so this is a standard trick for defining topologies, but it's usually not very illuminating. And again, I emphasize here, we're in the world of compact metric spaces. So a perhaps more concrete way of thinking about it is define the topology in terms of the convergence it implies. This is an equivalent way of defining a topology. Is that measures converge in this topology if and only if their integrals against continuous functions converge. That's for all continuous functions. All right, so again, this is a little more concrete, but would take a while to check this because you have to check the integral against every continuous function, real valued continuous function. Another characteristic, it just has to do with measurable sets. If you look at all measurable sets who have a frontier with zero measure, all right, then it suffices to show convergence of the measures of those sets. All right, so if we have such a set, I say below, if this is the topological frontier. If you this characterization makes A what's called a continuity set. So if the measures of continuity sets converge, then the UNs converge in the weak star topology. All right, now there's also a metric. So the space, the weak star topology is also a metrizable topology, and here's a metric that gives rise to it. You're given two probability measures. This is the sum 1 over 2 to the n trick. You take the difference. So, well, the first step here, which I skipped here, is we pick a countable dense set. So this is where very strongly we use the fact that X is compact metric and therefore CX is separable. So there's a countable dense set. All right, and then we define a distance by, we integrate the two measures against each alpha n, see what that difference is, divide by 2 to the n, and add these up, and then there's this normalization factor here. All right, so this gives rise to a metric. Again, you can check that. So here's a nice concrete example. If we look at the shift, then I'm not showing many of these things today, I'm just stating them, but if you look at the indicator functions of cylinder sets, that's in fact dense. All right, and so if instead of integrating the cylinder set, we remember that the integral of a cylinder set is just the measure, then the distance between the two measures is the sum of the differences of the measures of the cylinder sets. So this is Cn. So we've enumerated all the cylinder sets, and we take the difference that the two measures give to those cylinder sets, take the absolute value, and sum it divided by 2 to the n. All right, so this term is always 1 because these are indicator functions. So the max is always 1. Now, it seems a little strange, if you haven't thought about this, that indicator functions should be continuous. All right, so usually an indicator function, like if we're in Lebesgue measure, you know, the indicator function of even an interval is a flat top function, so it's definitely not continuous. But it's because the shift is totally disconnected. And therefore, in fact, the cylinder sets are open and closed. So in fact, that implies that they're continuous. So if you've thought about these shift spaces, this isn't surprising. If not, then maybe I'll assign that as homework, that the cylinder sets are both open and closed, and therefore the indicator functions are continuous. Okay, so there's an even more special case, which is the one that's going to concern us, is just thinking about invariant measures. So eventually we're going to restrict to invariant measures because they're the ones we care about. Remember that when we shift a cylinder set, we just shift where it starts. That's what this says. And also, this should be a minus here. That when we shift these guys and compute the measures, and we should have measures here. So these are bad looking mu's, but it tells us that when we shift the base or the starting point of the cylinder set, we get the same measure because it's invariant, and therefore we get this is equal to this. So it means we don't have to consider the measures of all the shifted copies of the cylinder set. We only need the one based at 0. All right, and so the way you do this is just enumerate the blocks. All right, so here's 0, here's 0, 1, 0, 0, 0, 1, 1, 1, 0, 1, 1, 0. All right, so this is enumeration of the blocks, and then we take the measure of the block by taking the measure of the cylinder set containing the block, and then take that difference and sum it and over 2 to the n. All right, now so that's an example. Another important property, again, I'm skipping a lot of proofs here because this is standard functional analysis. It should be believable, but the space of probability measures is compact. All right, so this will turn out to be very important in working. Of course, you all know how important it is to have a compact space. But with the weak star topology, the collection of Borel measures is compact. All right, so if you know more functional analysis, there's a famous theorem that the dual ball is compact, and that implies this. But let me not get too far into the functional analysis. All right, so the space of measures, we're not talking about invariant measures here, except we're in the example here. The space of measures, probability measures, Borel probability measures with this topology. Now there are other topologies. Notice it's called the weak topology, and so one can imagine there's a strong topology which may have other properties. All right, and so we want to talk now about invariant measures in this context. So now let's restrict to a continuous function of a compact metric space. And remember, basic property of continuous functions is the inverse image of an open set is open. And that implies the inverse image of the Borels is contained in the Borels. And that tells me that I can define a map, F star, from the probability measures to the probability measures by F star of mu equals mu of F inverse of B. All right, so I actually told you about this before in a similar context much earlier in the course, but now we have a continuous function which we need to understand the connection of the Borel measures, of the Borel sigma algebra. All right, so again, measures push forward. We have a measure here. All right, so you have a measure here, and you want a measure over here. So to figure out the measure of a set over here, you bring it back and compute its measure. All right, so if you think about it, you might want to go the other way, but if you do f of b and try to pull back a measure, unless it's bimeasurable, then you're not going to get a measure. All right, I'll also remind you about change of variables, that if you integrate against f star of mu, it's the same as the integral of alpha composed with f. All right, so this is where you have alpha coming out of here. So you have your map alpha here into the reals, and it says you pull it back to this guy by f. Remember, f is going like this. That if you pull it back here, then you integrate, the pullback is the same as integrating with respect to the push forward measure. All right. So this is starting to look like dynamics. We have a self map. Now it's continuous, and it induces a self map on the space of probability measures. All right, so standard mathematical thing, have a map on a space, induce a map on some larger collection of objects created from the space. All right, and we have a topology on this guy. And so now we can ask about the continuity properties of this push forward operator. And in fact, it's continuous and affine. All right, so let's see the proof of that. So let's assume we're going to show that the image of a convergent sequence converges. Since these are metric spaces, that suffices for continuity. So let's assume that the measures converge in the weak star topology and pick some alpha. And then we use the change of variables, and we're going to use what we have above. So the integral of df star mu n is change of variables, is this integral. And since this is an observable and mu n converges to mu, the integral of this observable converges to this integral of this observable. But once again, change of variables, this is alpha df star mu. All right, so this holds for all alpha. All right, so remember, if it holds for all alpha, this implies then that we have this convergence of this measure. All right, so again, this guy is converging to this guy. That's true for all alpha. That implies the convergence of the images of f star, and that's enough to get f star continue, again, because these guys are metric spaces. All right, for affine, it's pretty easy since measures are linear. So let's pick some p in 0, 1. We look at a convex combination and look at f star acting on that convex combination. Then by definition, we're using linearity here. p mu of f inverse of b plus 1 minus p mu of f inverse of b, and then just use the definition again. And this is p f star mu, 1 minus p f star mu of b. All of b holds for all b, and therefore it's affine. All right. Okay, so it's not, right, it's affine in the sense that convex combinations go to the same convex combination. All right, so now we have the dynamical object is the collection of fixed points of f star. All right, so now we look at all Borel probability measures which are fixed by the induced operator of f, the f star operator, the push forward operator. All right, so dynamically it's a collection of fixed points, and let's see what it means. It means if you're in this collection, then mu of f inverse of b equals mu of b for all b, but we've seen this definition many times. This is the definition of invariant measures. All right, so this structure here, this set here, is the collection of all Borel probability invariant measures. All right, so here's a useful condition for checking it's an invariant measure in terms of integrals. All right, so this is another characterization of this collection of invariant measures. It says that if you start with a probability measure, then it's an invariant measure if and only if, when you integrate alpha composed with f d mu, it's equal to the integral alpha d mu for all alpha in the continuous functions. All right, so one way, let's say we have an invariant measure, so that tells us that f star mu equals mu, then this integral equals change of variables, integral of alpha d f star of mu, but f star of mu equals mu, so this equals that. All right, so this equality here, going back, says, again, change of variables, says that alpha d f star mu equals alpha, there's a d here, d mu, and that's true for all alpha. So the integral against this measure and this measure are the same for all alpha, but that tells me that this measure equals this measure, and that's exactly saying that it's in the space of invariant measures.